In this final example, we've got soft serve ice cream. It's being poured into an ice cream cone at a rate of 1/2 cubic inches per second. The cone has a height of 6 inches and a radius of 4 inches at the top. And we want to know what is the rate of change in the height of the ice cream when the height of the ice cream is 3 inches. So, wondering about this problem, we circle our values. So we know something about the rate. It's 1/2 cubic inches per second. We know the radius of our cone, or sorry, the height of our cone is 6 inches, and the radius of our cone is 4 inches. And we want to know what is the rate of change when the height of the ice cream is 3 inches. So underlining our question, it is find the rate of the change of the ice cream when the height of the ice cream is 3 inches. And boxing our math terms, it's being poured. So coming in at a rate, so that's a derivative. The cone has a height of 6 inches, so that's going to give us a variable and a radius of 4 inches, and we want to know the rate of change of the height. So that's another derivative. And getting rid of excessive bits of information. Again, it looks like most of these is just factual stuff. So we've wondered about the problem, and now we need to organize all the facts that we've gathered above. So first off, we've got an ice cream cone. So let's, before we start anything, let's just draw a cone. So a standard cone looks maybe something like this. And we know that the height of the cone is 6 inches. So the height of the cone is, say, 6 inches. And the radius of the cone is 4 inches. So that's the radius. And ice cream is being poured in. So we've got ice cream coming into the cone, filling it up. And so at any given time, right, the ice cream will have some filled up the cone. And so we'll say it's filled it up. So this is all ice cream in here. And we want to know, find the rate of change of the height of the ice cream. So we're going to have our height of our ice cream, say right here. That's our h. So that's the height of our ice cream. So that's our first variable. Let's write it down, what it is. H is height of ice cream, of, say, ice cream. So H is the height of the ice cream. We, what else do we have in this problem? Well, the ice cream is being poured into the cone at a rate of 1/2 cubic inches per second. And at first blush, it might be not clear what this is, but the units give a hint, right? It's cubic inches. So this is a volume. The rate of change of the ice cream, the change in the volume of the ice cream, is 1/2 inches cubed. So I'm going to write that right here. dV dt is equal to 1/2 inches cubed per second. And since I've now introduced a new variable, v. I need to describe what it is. So v is the volume of the ice cream. And so have I collected all my information and gathered it together? Well, I've got change in volume. The cone is 6 inches. Use that. The radius of the cone is 4 inches. And, oh, I need to add this in. What do I need to find? I need to find the change in the height. So what is dh dt? What's the change in height of the ice cream when h equals 3? Right? This is the question being asked. So I'll box it so I can always come back and remind myself this is what is being asked in the question. This is the value I am after. All right, so we have organized all the facts, and now we need to relate our variables. So how is v and h related? Well, I know an equation that volume is equal to 1/3 pi r squared h. Now you may be asking, where did that come from? Well, dig back in the back of your mind, back in pre-calculus, you've probably seen this equation. Definitely in geometry, you saw this equation. But let's just say you don't know how to access it in your brain. Not a problem. We can search the internet. If you're at home doing a homework problem, you're like, oh, I need to know the volume of a cone. Simple search will give you that. If we're in a classroom, you can ask me. Anyways, so we have our relationship. The volume equals 1/3 pi r squared h. And notice, whoa, we've introduced another variable, r. This wasn't in the problem, but the problem forces our hand. We have to introduce this second variable. Well, what is that? That's the radius of the ice cream in the cone. So r is the radius of the ice cream. Right? The radius of the ice cream. So I make sure that I write it down what it is. So when I'm working the problem and I've totally forgotten what my variables are, I can always come back and remind myself, oh yeah, that's what it is. So, okay, we've wondered about the problem. We've organized our facts together. We have related our variables together. Now we need to decide how we will solve this problem, and it's a related rates problem, so we're going to use implicit differentiation. That's our number one go-to for a related rates problem. So let's start doing the math. So I'm going to take the differential of v. So dv is equal to the differential of 1/3 pi r squared h. And I'll take this a little bit slower than we have in other problems, right? This factor, or the differential, passes right past these constants, right? 1/3 is a constant, pi is a constant. So this is pi over 3 times the differential of r squared h. Now r and h are both variables. I've named them. H is the height of the ice cream, which is definitely changing as the cone fills up. And r is the radius of the ice cream, which again is changing as the cone fills up. And so I've got to use product rule. This is pi over 3 times, so product rule is h d r squared plus r squared dh. Right, that's just the product rule. And then dr squared will be 2h. So I can write that down here, that dv is pi over 3 times the quantity 2 RH dr plus r squared dH. And I want to know what is dH dt. So once I've differentiated and I've got down to all my basic differentials, I'm going to divide everything by dt. So this is divide this by dt and divide this by dt. And so I get that dv dt, so this tells me that dv dt is equal to pi over 3 times the quantity 2RH dr dt plus r squared dH dt. So now we have the derivatives, and we know that dv dt, we'll replace this in a minute, but that dv dt, we know a little bit about it, right? dv dt is 1/2 inches cubed. So I'll be able to put this right here. Right? This is equal to 1/2. They're one and the same. Okay. Now we want to know dH dt. I can replace dv dt with 1/2, but I can't replace dr with anything. Right? What is this dr business? I don't have any information. If I come back to the problem, remember we didn't know anything about radius. We're not told any information. We're just told that the rate of change of volume. We don't know the rate of change of r. So this means that we need to kind of backtrack a little bit because we've gotten to a place we're going to work through and we've got this dr dt to mess with. So something that should be tickling at the back of your mind is the fact that we've never used this information about that the cone is 6 inches high and that its radius is 4. That was information given us to in the problem. Now it could have been extraneous, but it seems suggestive that this relationship may give us a helpful relationship about R and H. And sure enough, if I look at this, I've got that these similar triangles, right? Inside of this cone, I've got this triangle out here, which has a height of 6 and a base of 4. And in here, I have a triangle whose radius is r and height is h. So let me draw this down here. This is going to kind of be a side project to get a handle on dr dh. So drawing this out, I've got this outer triangle, which has height 6 and base 4. And I've got my inner triangle, my ice cream triangle, which has base r, right? That was our radius, and height h. Same triangle, so that's height h. And the great thing about similar triangles, right? These are both right triangles. One is inscribed in the other. So the great thing about this is that r over h, if I take that ratio, it has to be the same as the ratio of the outer triangle, 4 over 6, which tells me that r is equal to 2/3 h. So that's a relationship between r and h, and from that, I can take the derivative of both sides, so dr dt is equal to 2/3 dH dt. So now the rate at which the radius changes over time is related to the rate at which the height changes over time. And I can take this now and put it in for dr dt. So that was a little bit of a side project to get a relationship. We know dv dt is 1/2, so I'm going to go ahead and write that. So 1/2 our dv dt is equal to pi over 3 times 2 RH times 2/3 dH dt plus r squared dH dt which is equal to pi over, well, actually, I'm going to do something here. I know most of you don't like fractions, so I'm going to factor it out. So this is pi over 9 times the quantity 4RH plus r squared dH dt. So if I did a few too many steps for you in regards to algebra, go ahead and go slowly. But all I did is I had a 3 here, so I factored out. So 3 times 3 is 9. Of course, I'm going to factor out a third here. I've got to factor out a third there, which I'm glad I just talked it through because this is wrong. Good, you should be scratching your head. How did he do that? Oh, right, when I factor the 1/3 out here, I need to get a 3 there. So this is plus 3 r squared dH dt. So even I make mistakes in my algebra, but I do try to go back and make sure everything made sense here. So dH dt, if I want to solve for it, right, I've got that 1/2 is equal to pi over 9 times quantity 4RH plus 3r squared. And so this tells me that dH dt, right, that's what I want to solve for. And so I'm going to multiply both sides by this. Is going to be 9 over the quantity 2 pi times 4RH plus 3r squared. And there's my equation for dH dt. Great, I finally arrived at an equation. And scrolling up, what do I want to know? What is dH dt when h equals 3? So the problem we're trying to solve is what is dH dt when h is 3? And as we found in many of the other problems, I look on the right-hand side, I've got multiple variables. I've got both r and h, not just h. And so I need to figure out what is r when h is 3. But we actually derived that earlier on. We know that r is equal to 2/3 h. So kind of doing our side work here, that when h is 3, r is equal to 2/3 times h, so that's 2/3 times 3, which is 2. Okay, so we know what r is when h is 3, so this equation then becomes 9 divided by 2 pi times 4 times 2 times 3 plus 3 times 2 squared. And what is all of that? Well, this is 9 all over 2 pi. And here we've got 6 times 4, so that's 24. Plus 3 times 4, which is, so that's 4 times 3, that's 12. Which is equal to 9 over, so 24 plus 12, that's 36, so 2 pi times 36, and I know that 9 goes into 36 4 times, so this is 1 over 8 pi. And what are my units? Well, h is in inches, so this is inches per second. So writing out my answer, what's the question? Question is, find the rate of change of the height of the ice cream when the height is 3 inches. So I would write something like, when the height of the ice cream is 3 inches, the height is changing at a rate of 1 over 8 pi inches per second. And that would be my solution. Now, I want to present to you an alternative approach. It's all very related, but all the way up here, we derived everything and we kept r's in place. But at the very beginning, we could have instead, if we had a little foresight, said, oh, well, r is equal to 2/3 h. So let me change my equation for volume. So this is an alternative approach. So in this particular problem, we know that volume is equal to 1/3 pi r squared h, and we know that r is equal to 2/3 h. So we could have substituted this in at the very beginning, right? So we would get that volume is equal to 1/3 pi times 2/3 h squared times h, which is, so 2/3 squared, that's 4, and this would be a 9. We've got this other 3, so that would be 27. So we would have 4 pi over 27 h cubed. Now, right off the bat, we've got an equation for volume that's only in terms of h. Now, that does require that we knew at the very beginning that we could make that relationship. So just as a suggestion, I mean, either we've got the right answer, 1 over 8 pi inches per second, but just an encouragement, anytime you have when you relate your variables in here and you've got multiple variables, right? We had 1, 2, 3 variables in here. And so this means volume is a function of 2 variables. Well, this is single variable calculus. So somewhere in the back of your head, a little flag should go up and says, we've got too many variables. Can I get another relation between r and h, which is what we arrived at, that r is equal to 2/3 h. And so we've reduced this problem down so that it only has 1 variable. And now going through the problem, right, dv is equal to the differential of 4 pi over 27 h cubed Differentiating, it goes past the constant. This 3 comes down to my new coefficient, which will cancel with the 27. So this is 4 pi over 9 h squared dh. Dividing by dt, we get dv dt is equal to 4 pi h squared dh dt. Solving for dh dt and knowing that this is equal to 1/2. So I get that 1/2, well, I'll do it this way. 1/2 is equal to 4 pi h squared, all divided by 9 dh dt, which tells me that dh dt is equal to 9 all over 8 pi h squared. And so dh dt, when h is equal to 3, would be equal to 9 over 8 pi 3 squared, which is 9, and we get 1 over 8 pi inches per second. So same answer, that's good. Means that that's a good double check. But also notice that the calculus here was much easier, but it did require the foresight to replace r with some equation in terms of h. So again, I encourage you, when you work these problems, and if you have more than 2 variables that are related, you're going to need another equation that relates some of the other variables. So that's just some advice. But even if you didn't have that foresight, you still would solve this problem because your hand would have been forced right here. You're like, oh, I got this dr dt, I don't know what to do with. All right, so I hope that that gives you some sense of how to work at related rates problems. The best way to get good at math is to do math. So the best way to be proficient at related rates problems is to work your hand at related rates problems. Best of luck and see you next time.